Next up, we have Aggie Smolinska, who's assistant professor at Maastricht University. So Aggie has a chemistry background, studied in Poland and the Netherlands. During her PhD, she worked in metabolomics using NMR and GCMS with advanced machine learning techniques in biomarker discovery of neurological disorders, mainly in multiple sclerosis. She did a postdoc at Maastricht University and at Dartmouth University. And the current research group at Maastricht is focused on multiple applications, including lung disease, chronic liver disease, inflammatory bowel disease, colorectal cancer, and IBS. Primarily using VOCs in exhaled air, but also other biofluids, and find relations to the gut microbiome using machine learning and multivariate statistics. Also, since 2020, she's been working and collaborating with us here at Alstom Medical for further development of breath research for, again, a whole host of different applications. So thanks, Aggie. Her talk is Exhaled Breath as Early Predictive Signatures of Asthma in Children. Over to you. Thank you.
Good morning, everyone. My name is Aggie Smolinska, and I'm working as assistant professor at the Department of Pharmacology and Toxicology at Maastricht University in the Netherlands. First of all, I would like to thank the organizing committee for giving me this opportunity to present our recent work that we do on asthma in children. But before I start with my presentation, I would like to introduce our team at Maastricht University, the XR team that we call it, which consists of people with different background, chemical and mass spectrometry, machine learning and data analysis, but also biomedical toxicology and the clinical. Within the team, we also have a lot of collaboration within Maastricht, but also outside Maastricht University. And because of that, we have very broad application of metabolites, volatile metabolites. So we do a lot of headspace analysis, dynamic headspace analysis, not only of cells, but also of bacteria. Next to this, we also do a lot of work with animals. For instance, we work with sheep, but we also do a lot of mice experiments where we basically study the development of sepsis, and we look at exhaled breath of mice. Obviously, next to in vitro and animal experiments, we do a lot of research on humans. So we look at exhaled breath, but also at other biofluids, where we look at volatile metabolites in various diseases, including respiratory and airway diseases, liver diseases, GI tract diseases, and we also investigate different diet interventions. But what I want to talk about today is asthma in children. As we know, asthma is chronic disease of the lung, and this is the most common chronic disease in children, and it has different symptoms, including wheezing, a shortness of breath, coughing. Of course, all those symptoms do not appear at once, but in children, they do not necessarily mean that this leads to asthma diagnosis. And the cause of asthma in general is really unknown, and we cannot cure it. If we look at the world prevalence of asthma, it varies between 5 and 10%. But what is it about asthma in children? Where is the problem? So the problem is that asthma can be properly diagnosed at age 6 years. And this is because of the lung function test that is used to diagnose asthma, that with small children is very difficult to perform. Therefore, what is happening is that asthma is mostly diagnosed using just symptoms. And that causes a problem. And the problem is that a lot of children are basically overdiagnosed. Overdiagnosed means that they are being treated unnecessarily, so that they receive different treatments such as corticosteroids, even if they do not have asthma. So therefore, what I will be talking about today is I will be talking about preschool asthma. So how can we improve diagnosis of asthma in preschool children? And this study has started in 2007 when we were asked to participate in asthma detection and monitoring study, ADAM-1 study, where we recruited 252 children and we collected exhale breath of those children, not at one time point, but it was collected over 4 years while the children were getting older. And at age of 6 years, each of the child was classified to one of the group, either healthy, wheezing, or asthmatic. And what we were interested in, we were interested to look, okay, can we use exhale breath to see is a child wheezer or is a child asthmatic? So let's look at some results that we obtained from that study at that time. So using a random forest machine learning technique, we were able to select 17 volatile metabolites in breath of children that were able to differentiate between asthmatic, healthy, and transient wheezing children. And what you can see on this figure is basically the main results that we obtained in the study, where you see 3 groups of points, blue points corresponding to healthy children, red points corresponding to transient wheezing children, and the green points corresponding to the asthmatic children. Each point here corresponds to one measurement for the child. So as you can see here, we have a lot of measurements. We have more than 1,000 samples here. And we see a clear trend. Of course, the separation is not perfect, but we can distinguish healthy, transient wheezing, and asthmatic children here. But of course, here we took all the measurement of all time points. But we were particularly interested in preschool children. So the question is how the 17 volatile metabolites in exhale breath behave if we take children at age 2 years. This is what you can see here. So we perform the similarity partially square discriminant analysis using those 17 volatile metabolites, and we wanted to see if we can distinguish wheezing and asthmatic at age 2. And you can see that the samples really cluster with respect to the group that they were belonging. So the stars to wheezers and the squares to asthmatic. But of course, we should not make any conclusion based on this plot. But if we look at the ROC curve of the validation samples, we see that we can predict asthma in preschool children with accuracy of 76% in validation samples. Looking at those results, we decided to follow up and to perform another asthma detection and monitoring study where we look at asthma and wheezer children, and we again collect breath of those children, but here our strategy is a bit different. So in this study, we really focus on the wheezer children. We collect breath, and using breath in combination with medical history and API score, we want to see if we can assign a child, a wheezing child, to treatment or to control group. Treatment group means here that the child is more likely to develop asthma in the future, and control group means a child is just a wheezer and won't develop asthma. So how do we sample children, preschool children, in ADAM-2 study? So we sample breath into modified Tetler bag. We have a mask and a filter. And as you can look at the mask, a mask has 2 inlets. And one inlet is connected to a filter, and another inlet is connected to Tetler bag. And while mask is put on a child's face, the child is inhaling through the mask. Air is passing first through the filter, going to child lung, and the child is then exhaling to the tether bag. When the tether bag is filled, the content of the bag is first used to do a sift MS measurement. The remaining part of the breath in tether bag is transferred to the carbon tube that are then used for the gas chromatography mass spectrometry measurement. So here we have two types of analytical technique. We have SIFT MS and we have GC-DOP MS. So in total, we have here 52 samples coming from the asthmatic children and 24 samples coming from the wheezing children. And as I said before, the main problem in preschool children is over-diagnosis and over-treatment. So here we would like to know which preschool wheezers will develop asthma. What is the probability of each of the wheezers to develop asthma? So if we have a data consisting of two classes, so we have asthmatic group and we have group of children which are just wheezing, our standard approach would be basically taking a classification technique and finding a border. So as you can see here, I have a red squares and a blue cycle. And using classification technique, either tree-based technique, discriminant analysis, supervector machine, or any other classification technique, I'm trying to find a border between those two classes. And depending on the technique that will be used, the border will look different. But in the next step, we want to assess that border. We want to assess our classification technique. And by doing that, we are looking how our predicted labels with our classification technique compares with our true label. And we can, of course, represent it as ROC curve, and we can look at our sensitivity, we can look at our specificity, and we can look at the area under the curve. But in our situation where we have wheezers children and we have asthmatic children, we have to take different approach. Why is that so? So imagine that if you have asthma children, they can be described with a certain distribution. The same is with our wheezer children, that they can be also described with a certain distribution. But what is important here, that those two distributions, they share certain part. And of course, this part is pretty unknown. It can be as shown in this figure, but this part can be larger. So if we have a new sample of a wheezer coming, I would like to know how similar the distribution of wheezer is to asthmatic distribution. So basically what I would like to know is the probability of developing asthma for each of these wheezer child. Therefore, the method that we used here is a one-class modeling. So this is not a standard approach where you take 2 classes or 3 classes and try to find the differences between those different classes. But here, what you do, you take each of the class, so asthmatic and the wheezer, and you basically model them separately. The method that we used here is called self-independent class analogy, SIMCA. But what we did, we made a modification to this method, and we created a technique that is called probabilistic SIMCA. So what we did here is basically we model asthmatic children here, and then we took our wheezers children, and we calculate a score. So a score of each wheezer to belong to the asthmatic. But of course, score doesn't tell us the probability. So in order to get a probability, we use a Bayes theorem to get the probability of each of the wheezers to develop asthma. So let's see some of our results. So if we look at our SIFT MS and the GCMS data, we start with PCA. So here what you can see is a PCA score for the SIFT MS data full scan mode, where the yellow cycles are asthmatic and the blue are wheezers. And if you look at here, of course, there's no perfect separation, but there is a certain trend. So if we look at the direction of the PC2 positive, we see more asthmatic. A bit similar results we see for the GC-TOF-MS, where again, yellow cycles are asthmatic and the blue cycles are wheezers. And again, samples on the positive side of the PC1 are more asthmatic. But of course, this is only PCA. And PCA doesn't give us any probability. PCA can tell us if there is any groupings in our data, if there are some outliers, if there is trend, but we cannot really get the probability of each of our wheezers of being asthmatic. So here comes our probabilistic SIMCA. So let's look at the results from probabilistic SIMCA. So first, what we do, we create a model for our asthmatic. So we do a one-class modeling of our asthmatic for the SIFT-MS data and for our GC-TOF-MS data. And of course, if you look at this here, there is, well, maybe nothing interesting. We see a lot of points here. But what is interesting now is to use those models, this one-class model of asthmatic, to see the probability of wheezer children to develop asthma. So if you look at SIFT-MS data, this is the results that we obtain. So each point here is a measurement obtained for wheezers, and the same comes for the GC-MS. But what is important is a color. So here you have a color bar going from the 0 to 1, while 0 means basically 0 probability of being asthmatic, and the yellow means very high probability, so 1, of being asthmatic. So we see here that we have wheezers children, that according to the probabilistic SIMCA, they have the high probability of developing asthma in the future. But of course, for those children, we do not have a real diagnosis. We don't have the gold standard, because those children here are the children at age 2. So we will get the diagnosis of those children in 4 years' time. But what we ask here, we ask three independent clinicians to make the diagnosis based on their clinical experience. And basically what we obtained is the following. So now you see the same figure as in the previous slide, but now next to the color, we see the name, and the names correspond to the diagnosis that the clinicians gave us. So transient means this child is not going to develop asthma, while asthma means that that child is going to develop asthma. And there is some interesting features here, or observation here. So for instance, if we look at this child here, so our probabilistic SIMCAs indicated that that child is having low probability of developing asthma. And if we look at the prediction, that diagnosis that we got from the clinician is exactly the same. Clinicians say like, no, this child is not going to develop asthma. If we look at here at some asthmatic, we see again agreement. But there are some parts where there is misagreement between our probabilistic SIMCA and the clinician. For instance, if we look at this sample here, we see that our probabilistic SIMCA said like, well, this child has low probability of developing asthma, while clinicians, based on the clinical history, says like, no, this child looks like more as asthmatic. If we look at the results for the GC-TOF-MS, we see very similar pattern. But what is interesting is that there were some children for whom the clinicians were not able to give diagnosis. And one of the child is marked here in the red cycle. And as you can see here, according to probabilistic SIMCA for SIFT-MS or GCMS, that child has a high probability of developing asthma, while clinicians were, based on the medical clinical history, they were not able to give a diagnosis. And this basically leads me to the summary of my talk, that I hope I showed you that Excel breath can be used for estimating the probability of preschool children to develop asthma. I showed you a method that can be used for that, which is one-class modeling, but we made a modification to this technique to obtain a probability score for each of the sample. And of course, the study that I showed you here is just a very small study, and this is not end of the story. But we are going to go back to our first study from 2007, and we want to focus on the transit wheezing and the asthmatic. And we want to use it for calculating probability for new wheezers and combine it with the SIFT-MS. Because if using SIFT-MS and GCMS should give us better description of the wheezers, basically we will be using kind of multi-approach, not multi-omics, but multi-approach to get a better diagnosis of the wheezers. And with that, I would like to thank some people for help in the study, and of course you for your attention.
So we've got a few questions coming already. I wanted to just ask a quick one. Aggie, you mentioned that there's the 17 VOCs initially that had been identified. Was there a degree of overlap in some of the VOCs that Steve Fowler had mentioned in the previous talk? Do you know?
Yeah, some of the aldehydes. So I think he mentioned octanol, nonanol. It's also in the list. I did not mention the compounds because all the identification, I have to say, it's tentative identification, so it's not standard confirmed. So I don't want to put a list, put it like, okay, written in the stone, if I'm not 100% sure. So it's basically based on mass recognition, and that was the best hit for the mass. But there is some overlap, yes.
Yeah, and that relates back, obviously, to the earlier session as well about how do we, assure confidence in the idea of those compounds.
Exactly, yes.
So we do have a question from Karsten. So sphingolipids have been reported as asthma. So these can be measured in breath exhale condensates, but probably not in breath air. Do you have any experience regarding metabolic correlates in breath air and breath exhaled condensates?
I have never worked in exhale breath condensate, and indeed this compound cannot be measured in exhale air directly. The advantage of the exhale breath condensate is, of course, that you can also measure non-volatiles, and in exhale air, it's not directly possible unless we go to exhale breath aerosol. But there is a lot of literature around showing that there is certain correlation between the volatiles found in exhale breath and exhale breath condensate. But we have never worked on that. So.
And it's worth just mentioning that we at Alston, we've been doing a bit more work looking at exhale breath aerosol. So, as part of COVID research, obviously with the transmission of virus on the aerosol fraction, modifying some of our breath collection devices to capture not just the volatile fraction, but also that exhale breath aerosol fraction on the same receiver device, which you can then extract and do analysis on. Watch this space for some of the data and the work that we'll publish on that. So there's a question from Overnar. I think we have pretty much addressed it already, though. So on the ADEM studies, very important study. Thanks for the presentation. Which volatile metabolites are measured? I don't think this was stated. So I think that's essentially what you said. If you don't have 100% confidence in it, you don't want to put it up there. Is that a first statement?
Yeah, exactly. But to be honest, at the end, for the statistical approach, I mean, you don't really care so much about the name, right? You just want to be sure that in your two studies, if you are looking, that at least the mass pattern is the same. But if it's compound X named or XX. For the method working is not a problematic. Of course, for understanding and biology behind that and for developing test, it is relevant. But at that stage of the research, I don't think so. The name is so relevant. So.
A related question from Gudrun around the identification, but asking around the statistics that were used for those 17 metabolites. Was that a supervised method or unsupervised methods?
So SIMCA is a supervised technique, but this is basically like doing PCA per class, but per se it is a supervised technique.
One question from, I was wondering about, this is one of my favorite topics in breath research, so couldn't help. What do you think the impact is of sort of the variability of the symptomology in these patients on the breath biomarkers that you find? They tend to go through periods of symptoms and then recovery, and they see the clinicians at varying times. So how would you account for that, and what impact may that have had on your study?
Yes, Mark, you are totally right. The amount of variation that we see is enormous. You can see it especially with some compounds that basically that are not present there. Even for instance, acetone, we could not detect it in some of the patients. To account for that, of course, it's very difficult. What you can do is, if you have any information with respect to some symptoms or any, let's say, like metadata that could help you with the analysis, you could include it in your statistical analysis and like basically remove that source of variation. But if it goes in all direction, it's very difficult. So if you work with very small group size, for instance, what you often see that basically the variation that is not interesting for you, that not relates to the disease, is basically larger than your disease. That's often seen if you compare to healthy. I see it very often if I have healthy versus disease, and you would say, oh yeah, that is this comparison. But if your sample size is not big enough, the variation is so huge, the non-interesting variation is so huge that basically you can barely differentiate them. So the effect size is very tiny, so then you need larger sample size. But I think it's kind of like a challenge in any field. Not sure, Mark, if I answered your question.
Yes, you did.
It's
Excellent. Well, that's all the time we have for questions. Thanks again, Aggie, so much.
Thanks a lot.
That was great. Thanks a lot. Cheers.
Pleasure. Thank you.